Hello everyone, this is subhasmita mjaumdar and I am from IIPS DAVV Indore, India, and I am here to give you the solutions for our NAD internal questions. So starting from the first question, we need to integrate the function tabulated below using Simpson's rule, wherein the values of x and the function, that is fx, is given. Now what we need to do is that observe the function is tabulated at 10 points. Simpson's rule requires an odd number of points. We will use trapezoidal rule for the first 2 points and Simpson's rule for the rest. So if we integrate the function fx from the points minus 0.6 to 0.3, so we use this formula wherein the first 2 points have been given using trapezoidal rule and the next points or the rest of the points have been integrated using the Simpson's rule. So the answer that we get is 3.1. Heading for the next question, here we have been given the population of a city in a census taken once in 10 years. And what we need to do is estimate the population for the year 1925, 1975 and 1984. So here you can see that the year have been given and the population that are in thousands. So first we make a table wherein the year and the population has been given and we use the forward difference operator to calculate del f, del square f and del cube f. So as del cube f is nearly 0 and we can fit a quadratic and use only up to second difference, 1925 is near the top of the table and we use the forward difference formula like I said before. So here we use the formula like you can see. The formula that we use is this formula for forward difference. Here x minus x1 is equals to UH and x1 has been given to us as 1921. H is the difference of the years and x is equals to 1925 and therefore U is equals to 0.4 and we get the value of U by putting it in this formula. So the value of the function at 1925 is equals to minus 37 when rounded off. Again for the year 1975, which is near the end of the table, and thus we use the backward difference formula and the backward difference formula is given in here. So for the value of the function for 1975 as we calculate by using this formula, again we use the value of U, which is minus 0.6. So we get the value of the function for 1975 equals to 196, which has been again rounded off. Now we find the value of for the year 1984, which is outside of the table, so thus we cannot interpolate. But if we assume however that the function trend outside the table is the same as inside, then we can imagine continue using the same interpolating form polynomial. Now again we calculate the value of U, which comes to 0.4 and the value of the function for 1985 is 249 and we round it off again. Then heading for the next question, we see that we have been given various angle radians with a difference of 0.01, that is 0.25, 0.26, etc. and the value of sine for the same, and again we use the forward difference operator to calculate del of f and del square of f. So a portion of the table of sines is given below. It is required to find the derivative of this function at x equals to 0.27. So for x3 equals to 0.27. So we use this formula and we get the value of the derivative at x3 equals to 0.27 as 0.9550. The correct value of the derivative to 4 digits is 0.9638. We will now use a coarser interval. I will magnify a bit. coarser interval of tabulation and calculate the derivative again. So again, by using the same difference formula, we calculate del of f and del square of f, and we get the value equal to correct 4 decimal places, that is 0.9634. Then the second value obtained in above example is not surprising, as the difference of tabulated values are taken in differentiation, and if these values are close, there is a severe loss of significance. So since we want more of a significance, we use this formula. If there is rounding error of e in f3 and minus e in f1, then the error in the derivative due to rounding error would be this. We use this formula for calculation of error, which is due to rounding off. With 4 significant digits in tabulated values and h equals to 0.01, like I've told before, this error could be equal to 0.004. So r dash, we calculate the rounding error as r dash of x equals to, using this formula we get the value of r dash of x equals to 0.000016. Now heading for the next question, we have been given a set of equations like you can see, and we need to solve the above equation by Gauss-Seidel or Gauss-Jordan method. So, and we need to find out whether a row interchange is necessary or not. So I choose Gauss-Jordan method. So I have done the following steps to solve the equation using Gauss-Jordan method. First, I have set an augmented matrix, and then using Gauss-Jordan elimination method, there are 2 steps. We need to use forward elimination and back substitution, but practically it is more convenient to eliminate all elements below and above and once when using Gauss-Jordan elimination. And the third step is like you can see, it is important to notice that while calculating using Gauss-Jordan calculation, if a matrix has at least one zero row with non-zero right hand side, the system of equation is inconsistent. Then the solution of such system doesn't exist. So I have set up a matrix according to the equations that we have been given, and then make the pivot in the first column by dividing the first row by 2. By dividing the first row by 2, we get this matrix like you can see here, and then we multiply the first row by 2. So by doing this, we get this kind of a matrix. Then we subtract the first row from the second and restore it. So by doing this, we get this kind of a matrix. The values are here, and then we multiply the first row by 4. So by doing this, we are getting this, the matrix that we are getting is this, and then we make the pivot like you can see that in the second column by dividing second row by -3. So again, by doing the operation, we get this matrix. We eliminate the second column and then make the pivot in the third row by dividing third row by -6. So like you can see that we have got some number of zeros here. So finally we eliminate the third column. By eliminating the third column, the values for x1 is -55 by 18, the values for x2 is -20 by 3, and the values of x3 is -25 by 9. So then we use Simpson's rule, which is a popular numerical integration technique. It is based on approximating the function f of x by fitting quadratics through sets of 3 points illustrated graphically. So here we you can like see the graph, and here we use the Simpson's 1/3 rule. Thank you very much. I hope this was very useful for you. Thank you.